Hello guys, Mr. Pratama is here, and today I'm going to explain to you about stationary waves. This chapter is still talking about the waves. If previously we talked about the progressive wave, this time we talk about the stationary wave or standing wave. Now, so what is the difference actually between the progressive wave and also stationary wave? The progressive wave itself actually transfers energy from one place to another. Yeah, so the progressive waves is the kind of wave that transfers energy from one point to another point, while the stationary wave or standing wave does not transfer any energy. Okay, now guys, you also can open the slide that I give to you in the Google Classroom, which is actually this one. Okay, now it also says that the stationary waves occur by resonance only at the natural frequency of vibrations of a medium. It means, yeah, every single object actually have its own natural frequency. And if it reach the natural frequency, then the standing wave or the stationary wave will occur. If it is not reached the natural frequency, then the standing wave or stationary wave will not occur. Now, for example, yeah, a bridge. Okay, if a bridge being blown by the wind and then it reach its natural frequency when it's moving, then the bridge will form a standing or stationary wave. If this keep occurs, yeah, then the bridge might fall because why? Yeah, it reached already the natural frequency. The most simple example of a stationary waves, if you tie a rope into a pole and then after that you move the rope with exact same frequency for each seconds, then you will see that the rope is moving up and down and reach the pole, okay, the fixed point. Okay, so and then after that it will return to you. So there are two fixed points, you and also the pole. That's how a stationary wave can occur. Yeah, if let's say you do not tie the pole, the rope into the pole, yeah, then you will transfer your kinetic energy, yeah, from you to another point of the rope. But since you tie it into a pole, then this energy will reflect back to you. Okay, that is how a stationary wave can occur. So now you guys already know what is the difference between the progressive wave and also stationary wave. Now you can open the next slide. Okay, it says that a stationary wave have nodes where there is no displacement at any time. Okay, if you go back to the first slide, then you will see there is a point where that point it is not moving at all the time. Okay, you can also see on your textbook page 212. Okay, the nodes on a stationary wave will never move. Okay, between two nodes there will be antinodes. Okay, the antinodes is the point between the nodes. Okay, and then where the displacement has maximum amplitude. So it can be the maximum at the peak and also maximum at trough of the positions of the stationary wave. Okay, now again, if you could see here, okay, so this one the point, okay, the point here will never move. This point, the notes will never move. Okay, while this point between the notes, this is the notes, yeah, the point between the notes is the anti-notes. The anti-notes can move up and down. Okay, while the notes here will not moving at all. Okay, can you imagine it? A point. Okay, the point will not move. The point that is not moving is the notes, and then the point between the notes is the anti-notes. So every stationary wave will have it. I'll move on to the next slide. Now you know already that a stationary wave will always have notes and anti-notes. The notes, again, it will never move its position, it will stay, and then the anti-notes will move up and down only. Now, so all particles, yeah, between two adjacent nodes, yeah, one nodes and the next nodes, yeah, will always in phase. Okay, you know, right? In phase and out of phase, we have studied about the phase difference previously. Now, so the nodes are always in phase, never out of phase, because they are exactly in the same line. Okay, different position, same line, yeah, never move. Okay, now the waveform in a stationary wave does not move through medium. As I've mentioned to you just now, yeah, the stationary wave will not transfer energy from one point to another point. Okay, the energy is not carried away from the source of the energy. Okay, to be more clear about the positions of the nodes and also the anti-nodes, you can see here. Okay, this is the nodes, this is the nodes. Okay, you see, if I hold like this my hand, yeah, you will see that the nodes, the points of the nodes, this one will never move, this one also not moving, 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 the point, but the anti-nodes is moving up and down. Okay, that is how the nodes and the anti-nodes in stationary wave are formed. Okay. Now, going on to the next slide, okay, they are setting up an experiment, okay, while also I will give to you the link, yeah, of the experiment, so you can watch also the experiment later. Okay, now, from the experiment, we call it a smell days experiment. Okay, you can check it on the link that I provide to you. If not today, then it will be tomorrow. Now, this Maldays experiment, yeah, prove that the lowest resonant frequency will call the fundamental frequency. So every object, as I've mentioned to you also just now, every object will have its own natural frequency or fundamental frequency. Okay, now how to count this fundamental frequency? Let's say for a string. Okay, for a string we can count the fundamental frequency, yeah, by the formula that you can see on the next slide. F0 is equal to 1 over 2 times the length, yeah, times the square root of the tension over the mass per unit length. Okay, so it means every string, yeah, if it is different kind, different length, will have different fundamental frequency. Okay, you got it? Okay guys, now let's talk about the connection between this standing or stationary wave with musical instruments. The first example is guitar. Okay, now let's imagine I'm holding a guitar right now, and then after that I pull one of the string up. Okay, I pull one of the string up and it will looks like this one, right? Okay, if I pull one of the string up, it will looks like this one. Yeah, it means that the string of the guitar now making two notes, which is this one and this one, okay, and one anti-notes in the middle. Okay, now if I release the string, then it will move back and forth, right, up and down. It will form this stationary wave. Okay, those stationary wave that only have one anti-notes in the middle and two notes, we call it as the first harmonic. Okay, you can also see your slide now. The first harmonic of a guitar strings or any strings that you pick up, pick like that. Okay, the length of the string is half of the lambda. Why it is only half of the lambda? As you can see from the picture, it will only produce one peak, no trough. Okay, only one peak, no trough. So the length of the string is half of the wavelength, and the frequency will be F equal to V over 2L. Okay, following the formula that we have studied from the previous chapter, that frequency is speed over lambda. Okay, V is equal to V over L. In the same musical instruments, the guitar. Okay, following the first harmonic, the second harmonic will produce one peak and one trough. Okay, so it will produce two anti-notes and also three notes. As you can see also from the slide, there are three notes, 1, 2, 3, and two anti-notes, 1, 2. Okay, for that one, the length of the string is equal to the wavelength, so the frequency will be the speed over the length of the string. Okay, and then after that goes to the third harmonic. The third harmonic, okay, will produce three anti-notes and also four notes. The formula you can check also from the slide. And then after that, the fourth harmonic or the third overtone, it will produce four anti-notes and five notes. And then next, the fifth harmonic or the fourth overtone, it will produce five anti-notes and six notes, and so on. So guys, the fundamental frequency of the string only for the first harmonic. Okay, remember that the fundamental frequency of the string is only for the first harmonic. For the second harmonic, it will be twice as the fundamental frequency. For the third harmonic, it will be thrice as the fundamental frequency, and so on. Okay, after this, I want you guys to take notes from the video that I gave you yesterday from Professor Dave, and also take some notes from the slide. Okay, only important things, and then you also need to submit it to me today via Google Classroom. Thank you and bye-bye.